Hello, students, can you hear me? Okay, fine. Okay, fine. So, good morning, all of you. So, let us start today's class. So, we were talking about the weak slot and filler structures in yesterday's class, right? So, what is a weak slot and filler structure? Basically, slot means an attribute and filler means its value. Okay, so we are trying to basically link the attributes to their values. That is why we call it as a slot and filler structure. Okay, slot means an attribute, filler means its value. So basically, if you are trying to fill a value in a attribute, then we call it as a slot and a filler structure. So basically, a structure which supports the property that you can get the value of an attribute through property inheritance, that is called as a slot and filler structure. Okay, so so basically there are two types: weak and strong. Weak slot and filler structure and strong slot and filler structures. So weak slot and filler structures, we have semantic networks and frames, and strong slot and filler structures, we have conceptual dependencies and scripts. So that we will study later. First of all, we will study weak slot and filler structures. So, as I told you, it is a structure which supports inheritance, right? So, there are some few good points about this, weak slot and filler structures, that they use object-oriented programming. Okay, so they will use the concept of reusability. For example, if you have a property of a particular superclass, then that will be inherited in all the subclasses. So basically, they can reuse the properties which are common in the main class, in the superclass. So that's a property of object-oriented programming, which is also there in the weak slot and filler structures. Other property is that the relations can be described easily using some higher order logic. So basically, if you want to describe the property of some relation, for example, I say that example that I say that the team of this ABC person is India. So that is basically a relation, that the team is basically the relating thing between subject and object. Subject is ABC, object is India. So basically your team is the relating thing between the subject and object, right? So in order to describe this relation easily, you can use the weak slot filler structures, or you can say semantic networks. And the other important thing is the weak slot and filler structures. Basically, they index the sentences by the entities. Okay, so if I'm saying that the team of ABC is India, so basically that entity that it is describing, there are two entities involved. One is ABC, other is India, right? So the indexing would be done using these entities. So it will be using ABC or India. So basically, you will be storing these entities somewhere to represent this sentence. So if you want to retrieve the value of an attribute of an entity, for example, if I want to say that what is the value of the team, so it will basically tell you that the value of the team is India. Basically, it is the Indian team. So retrieving the value of an attribute of an entity is faster because you have done the indexing by the entities only. So if you have done the indexing through the entities. So if, whatever sentence you have, that entities involved in the sentences are the entities which are involved in the indexing also. So it's easy to retrieve the values of the attributes. So if I say what is the team of ABC, since you have an index with ABC, you can quickly get that ABC is involved with India. So it's related with India. So you'll get the attribute value as India, like this. So it's easy because there's a network which is basically connecting the attribute to its values, and you are basically that value and attribute both are the entities which are indexed in the index. So these are some properties of weak slot and filler structures. Now the first one is semantic network. So we'll study the first one first of all. So what is a semantic network? It was introduced by Quillian, and it's basically a structure that represents the knowledge in a graphical form. Okay, so it's basically the main concept is it uses inheritable knowledge. So if you want to basically inherit certain kind of properties of an attribute, or the attributes, that can be done in the semantic network. So it's based on inheritance. So it is basically Sentence is one powerful knowledge representation mechanism which we actually work upon in a semantic network. So basically, a semantic network is a network which is representing your sentences in a graphical format, right? So what is that graphical format? Basically, you have objects, and suppose you have a subject and an object, so they will become the entities, or you can say the boxes or the nodes. So basically, semantic network is a network which consists of labeled nodes and the links between the nodes, right? So objects are denoted by the nodes, and the relations between the objects is denoted by the link. Okay, so objects are denoted by a node, and the relations between the two objects, that is denoted by a link. So if I say that the relation between the two objects, so basically it can relate the subject and the object like this. So it is a network structure that we formulate. So I'll give you an example. Let's see, this is my semantic network. Let's say this one. So this semantic network, we had also discussed when I was telling you about inheritable knowledge. If you remember, this semantic network is the same network which we had discussed at the time of discussing about the types of knowledge. So under inheritable knowledge, we had actually discussed this network. Okay, so what is this network saying? Basically, if you interpret this network, there are certain node and there are certain arrows. Arrows means links, right? So nodes here are actually representing the attributes and their values. So for example, let's start with the lowermost node, Rohan Shukla. So Rohan Shukla is basically an object, or you can say it's basically Rohan Shukla is basically your class, and team, it's basically connected with Delhi Royals. So Delhi Royals is basically the team of Rohan Shukla, right? So you can also say that Rohan Shukla has is basically your attribute, and basically your so basically your object, and this is your attribute team, and the value of this attribute team is Delhi Royals. So Rohan Shukla is your object, and the team is your attribute, and the value of this attribute is Delhi Royals. So basically, this is value of an attribute and the object, so that are basically represented by nodes, and the attributes are basically your relationships between the objects and the value of the attribute. So that is represented as an arrow. Okay, so the meaning of this is the team of Rohan Shukla is Delhi Royals. Similarly, if you see on the right hand side, it means that Achint Tiwari's team is Pune Champs. So the team of Achint Tiwari is Pune Champs. Similarly, if you go up in this hierarchy, in the semantic network, so you'll say, if you consider bowler, then so bowler is a class, or you will say an object of a class, and it has got an attribute batting average whose value is 30.5. Similarly, you have batsman, which has got an attribute batting average and its value is 59.58. So bowler's batting average is 30.5 and the batting average of batsman is 59.58. Similarly, you can go up and you can generate the sentence forms of all these network representation. So Indian player's height is 6'1" and the batting average of Indian player is 42.23. This is the meaning of this representation. Then if you go to the up in the hierarchy, Asian player, so Asian player's height is 5'8". Then if you go the topmost, it's cricket player object. So you can get the sentence representation of this object as the value of handed for the cricket player is right. So basically cricket player is handed right. Okay. So these are basically the simple sentences which you can formulate using this semantic network. Now, two more relationships are there which are also very important. Those which I have not discussed till now. So those are instance relationship and the ISA relationship. Okay. So what is an instance relationship? We had already discussed this, students. So basically an instance relationship is a class membership relationship, and ISA relationship is a class inclusion relationship. Okay. So if I say Rohan Shukla is an instance of bowler, this means that Rohan Shukla is basically a member of the bowler class. Similarly, if you say Achint Tiwari, so if you say Achint Tiwari is an instance of batsman, this means that Achint Tiwari is a member of batsman class, right? So it's basically an instance of bowler. Rohan Shukla is an instance of bowler and Achint Tiwari is an instance of batsman. Okay, so it's a class membership. But if you see is a relationship, that is a class inclusion. So bowler is included in the Indian player. So if he is a bowler, he is an Indian player. That is obvious fact. Okay. Similarly for batsman, if I say if he is a batsman, then he is an Indian player. So both bowler and batsman are basically Indian players. And then if you go up in the hierarchy, Indian player is a Asian player. So this is basically another relationship where ISA attribute is linking the Indian player and the Asian player. So basically, if you say the subject is Indian player, basically your object is Indian player, and the attribute is ISA, and the value of the attribute is Asian player. Okay. So if you interpret it in a normal sentence representation, it would be like Indian player is a Asian player. And then if you go up, Asian player is a cricket player, like this. So basically, this is the meaning of ISA and instance relationships. So basically, this is a simple network which you can easily convert it into a normal English representation of sentences. Are you to get this, students? What is the meaning of how do we construct this semantic network? What is the meaning of this network? Are you getting? Okay, fine. All of you, please respond more students. What about others? Are you getting what is the semantic network? Okay, fine. Okay, fine. So now if I want to represent this, for example, in a semantic network, as I told you, it's a way of representing the relationships and basically the relationships between an object and the value of the attribute of an object, right? So that is a semantic network. Okay, so generally we represent the binary predicates only in a semantic network, right? For example, if you see this is Rohan Shukla is the object and the attribute is team and the value of the attribute is Delhi Royals. So if you represent it in a format, in a predicate logic format, so it will be represented like this: team bracket Rohan Shukla comma Delhi Royals. So this will mean that Rohan Shukla's team is Delhi Royals. Okay, so that is basically a binary predicate. So it's having two arguments. So whenever we represent a semantic network in a predicate logic format, generally it will have a binary predicate. So because we generally a network is formulated between two nodes, right? So if you want to formulate a network that is generally between two nodes, so out of them one node will be the object and the other node will be the value of the attribute of an object. So that is why always the relationship will be between two nodes. And when you convert that relationship into a predicate logic format, it will always result in a binary predicate. Okay. So if you want to convert some of these nodes or some of these relationships into a predicate logic format, so let us try. So you can say team of Rohan Shukla is Delhi Royals. So it can represent it by the first form. Team Rohan Shukla, comma Delhi Royals. Now if I want to represent the batting average of bowler, so batting average bracket bowler comma 30.5. So basically whatever is your attribute that will come as a predicate, that will become your predicate, and the object will become your first argument and the value of the attribute will become your second argument. Okay, so basically the left hand side of the arrow where the arrow is beginning, that is becoming your first argument, and the right hand side of the arrow is becoming your second argument. Okay, so this is how you convert a semantic network into a predicate logic representation, right? So if I say, let us say I want to convert this relationship batting average of batsman is 59.58. So let us say if I want to represent this relationship in a predicate logic form, so it will become batting average bracket batsman comma 59.58. So that will be the representation in predicate logic format. So this is how basically you can convert your semantic network into a predicate logic format and from a predicate logic format into a semantic network, vice versa. Both are possible. So let's see some other representations. For example, if I say instance of Rohan Shukla, comma bowler. So basically this is what I am going to represent. See, in the last one, Rohan Shukla is connected to bowler through the instance attribute. So that particular portion of the diagram I am converting into a predicate logic format. So that's why I say instance bracket Rohan Shukla, comma bowler. Similarly, if I want to represent bowler is an Indian player, if I want to represent this particular part of the diagram, bowler is an Indian player in a predicate logic form. So that representation would be is a bracket, the left side of the arrow, comma, the right side of the arrow. So bowler, comma, Indian player, right? So is a bowler, comma, Indian player. So basically, whatever is your attribute, that becomes your predicate. Whatever is your object, that becomes your first argument, and whatever is the value of the attribute of the object, that becomes your second argument. Okay, so this is how you convert a semantic network into a predicate logic representation. Right, now I want to answer some queries. For example, if I say, what is the batting average of Rohan Shukla? Can anybody tell me how do I get the batting average of Rohan Shukla? So I want to get the batting average of Rohan Shukla from this semantic network. Can I get search using Rohan Shukla? How? So I have to start with Rohan Shukla and I have to move up in this hierarchy. First of all, I have to see that Rohan Shukla has got an attribute batting average. If it has got, then I will take the value from that attribute only. But Rohan Shukla doesn't have any attribute called as batting average, right? So then I'll move up in this hierarchy and I will try to find out whether because Rohan Shukla is an instance of bowler, so I'll see that whether a attribute called as batting average exists in the bowler class. So it is existing, right? So bowler is having a batting average attribute. So you will use the batting average attribute of bowler in order to get the batting average of Rohan Shukla. So that is through inheritance. Because whatever is the batting average of bowler, that will also be the batting average of Rohan Shukla because Rohan Shukla is an instance of bowler, right? So that's how you get the batting average of Rohan Shukla is 30.5. Okay. So that's through inheritance. You can get the answers to your questions through inheritance also. Now suppose you want to find out the height of Rohan Shukla. Can anybody tell me what will be the height of Rohan Shukla from this diagram? Can anybody tell me what will be the height of Rohan Shukla from this diagram? From this semantic network? Whether it will be, what will be the height? 6'1", okay. Any other response? Any other response? Okay, what about 5'8"? Why not 5'8"? 5'8" is also given as the height of Asian player. So why not 5'8"? Can anybody tell me why you have not taken 5'8" as the height and why you have taken 6'1" as the height? Okay, so basically, yeah. So basically, we stop when we find the attribute value upwards in the hierarchy. Okay, so as I go up in the hierarchy and I find the value of the attribute which I'm looking for, so I'll stop. I'll not go further up in the hierarchy. Okay, why? Because if you go further up in the hierarchy, then the result will become more and more general, right? As you go up in the hierarchy, you are actually going towards the super classes. So the result will become more and more general. So if you say the height of Indian player is 6'1", so if you take Rohan Shukla, he's not having an attribute height, so he'll go to bowler. But bowler is also not having an attribute height, so he'll go to Indian player. Now Indian player has an attribute height which has got a value of 6'1". So you will not go further. Why? Because if you go further and take the height of Asian player as 5'8", that will be a more general case because Asian player is a super class of Indian player. Okay, so generally we take the more specific answers. So the place where we get the answer, we stop there. We don't go further up because if you go further up, that will become more and more generalized answer. So we want more and more specific answers. So we generally start from the bottom, and whenever we find the value of the attribute we are looking for, we will stop. Okay, so this is how through inheritance you can get the answers to your query. For example, if I want to get the height of Rohan Shukla through inheritance, I can go up in this hierarchy and I'll get the height as 6'1" for Rohan Shukla. Fine. So if I don't get the height in Indian player also, then I'll go to Asian player and then I'll use this height 5'8". Okay. But if I've already got the height of Indian player as 6'1", then I'll not go further. So this is how through property inheritance you are able to achieve the answers to your query, or you are able to basically infer some things. Okay. So basically, I mean, this is called as inheritable knowledge. You are already inheriting the properties from the main class in the subclasses, right? So this is basic use of a semantic network, that through inheritance you can basically inherit some properties from the sub superclass into the subclass. Okay. So this is a basic semantic network and its conversion into predicate logic format. So if you have been given a predicate logic representation, you can easily convert it into semantic network, right? And if you have been given a semantic network, then you can convert it into a predicate logic representation, and that will be generally binary predicates only. Are you able to understand, students, how to convert semantic network into predicate logic and vice versa? Getting? Okay, fine. Okay, fine. So now, how do we represent non-binary predicates in a semantic network? Okay, so till now we have studied how do we represent a binary predicate in a semantic network. That is basically your object is one node and the value of the attribute is another node, and the attribute is basically the relationship which is linking the two nodes, right? So generally it is in the case of a binary predicate. But suppose you have an n-ary predicate, means you have more than two, basically it's basically having more than two arguments in the predicate. Okay, so then how do we generate a semantic network out of it? So what we do is n-ary predicates can be, we have to convert them into binary predicates. So at the end, always a semantic network is a basically representing a relationship between two nodes only. Okay, so always you have, in the end you have to convert every non-binary predicate into a binary predicate only, and then only you will be able to represent it in a semantic network. So always an n-ary predicate has to be converted to a binary predicate format only if you want to represent it in a semantic network. Okay, so how do we do it? What we do is we create one new object representing the entire predicate statement. Okay, so we create one new object that's not given to us, but we create it as our own. So that is our own creation of a new object that represents the entire scenario actually. Okay, and then we introduce the binary predicates to describe the relationship of each of the relationship of each of the arguments to this object. Okay, so basically what I'm saying is you create a new object and you link all the arguments to this new object. Okay, so for example, in this case, you have this score, Cubs, Dodgers, and 5-3. So there are three arguments. Okay, so what you do is you create a new object. Okay, so G23, if you see that diagram, G23 is a game. Basically, you are talking about the, basically what you want to represent here is the score of team. Cubs is basically your team, and Dodgers is your home team. These are two teams, and the score is 5-3. So basically, you are talking about a game, right? You are talking about a gaming scenario. So what you do is you create a new object which is basically the game. So you are calling G23 as an instance of a game. Basically, it is a game. Game is a object and G23 is a game. So basically, it's a specific game. You have created one node to represent the specific game. Okay. And now to this new object, you will relate all the three arguments. Okay. So Cubs, Dodgers, and 5-3. All of these would be related to this new object. So if you relate all of these one by one to this new object, then they will be binary predicates only, right? So in this way, you will be able to represent the non-binary predicate in a binary format, in a semantic network. How? So let's see. So as I told you, you have to basically connect each of these arguments to this new object. So if you connect Cubs to G23, you can say that the relation Cubs is the object and you are relating it to G23. So the relationship, or you can say the attribute, is basically the visiting team. So if you consider a game which is a specific game being played, there the visiting team is Cubs and Dodgers is the home team and the score is 5-3. Basically, that is the information that you want to represent. Okay, so the information in this predicate logic format which you want to represent is this only, that there are two teams, Cubs and Dodgers. So one of them will be visiting team, other will be the home team, right? So the match is being played between Cubs and Dodgers, and the score is 5-3. So the first team is having a score of 5, the other team is having a score of 3. Basically, that is the meaning of this predicate logic representation, right? So if you are writing just like this, score bracket Cubs, comma Dodgers, comma 5-3, the whole meaning is that there is a game being played in which two teams are playing, Cubs and Dodgers, and the score is 5-3, right? So that's the whole sentence meaning which you want to represent, right? So how do we do it? If you want to represent in the network form, so what we do is we consider that it's basically a game being played, so you create a new object for the game, okay, and then you relate all these three arguments to this new object. So then they will become binary predicates. So you relate each of these arguments to this new object. Then Cubs would be related to this G23, and Dodgers would also be related to G23, and 5-3 score that will also be related to G23. Fine. But the thing would be that is different is that they will have different relationships to this G23 game. So the Cubs is the visiting team, so its attribute name is visiting team. Dodgers is the home team, so its attribute name is home team, and the score is 5-3. So we have given an attribute called as score between G23 and 5-3. Okay, so this is how we convert a non-binary into a binary predicate format, and then you represent it. So a node is created to represent this specific game, and then we relate each of the three arguments to this new node. Are you able to get the students? Any doubt in this network? Any confusion? How did you do it? Is it okay? Is it okay, or you want me to repeat, or is it not clear? Please respond, students. Okay, I'll explain once again this point. So what I'm saying here is basically a non-binary predicate, right? So there are three arguments means it's a non-binary predicate. Binary predicate will have only two arguments, right? So now if I want to convert a non-binary predicate into a semantic network, I cannot do it naturally. That is not a natural representation. So natural representation of a semantic network is between two nodes only. Relations are always between two nodes, right? Not between three nodes. Okay. So we have to convert this non-binary predicate into a binary predicate. Then only we can basically use it into a semantic representation. So now how do we convert into a binary predicate? That is the main objective. Okay. So what we do is this whole scenario is actually a gaming scenario, right? Because we're talking about two teams, Cubs and Dodgers, and their score is 5-3. So it's basically a gaming scenario. So whatever is the main theme of this particular predicate logic representation, the main object. So you create a new object for that. So you create a new object for this entire predicate statement. So the entire predicate statement is that this is a game basically. So it's a game being played. So you create G23, which is a specific game. Okay, you can create an object game, but here you have created G23, which is a specific game, because game would be a general thing. But I'm talking about a particular game where Cubs and Dodgers are playing and the score is 5-3. So I'm talking about a specific game basically. So that is why I create another class which is a subclass of game, right? So that class I'm calling as G23, right? Because I'm talking about a specific game. I'm not talking about any game. I'm talking about a specific game where Cubs and Dodgers are playing and the score is 5-3. So that is why I create a subclass G23, which is a specific game, right? Now I've created this object G23. Okay. Now I have to relate it to each of the three pieces of arguments. So how I will relate? Cubs is the first argument, so I'll relate it to G23. Cubs is my object, then Dodgers is my object, and then 5-3 is my object. So all three I'll relate it to G23. So the relationships would be different for all the three. Okay, so what will be the relationship of Cubs? The visiting team. Cubs is the visiting team. So the relationship, you'll mark it as a visiting team. So on the top of this arrow, you'll write the attribute name, or you can say the relationship name as visiting team. And then for Dodgers, it's the home team. So you have plays a relationship name as home team. and then the 5 3 is basically your score. So that is why you place the relationship name as score. Okay. Now, one thing here is that, okay, till now, is it okay, students? Any doubt? One more question I want to ask. But before that, I want to ask that whether it is clear or not. Is it okay now? Are you able to get it? All of you? Yeah, that one, that question only I actually wanted to ask you. What is the direction of Dodgers? So, is this correct? Actually, the direction of Dodgers to G23 link. See here, G23 is your main object, which is connected to all the objects. Okay, so this is your main object, and it is connected to the basically the values of the attributes, right? So if I say G23, this is the object, and visiting team is the attribute, and Cubs is the value of the attribute, right? So always whenever you have a binary relationship, the object comes as the first argument, and the value of the attribute comes as a second argument. And there is an arrow from the left hand side to the right hand side, basically. I mean, from the starting of the arrow to the end of the arrow, right? So the starting of the arrow points to the object, and the end of the arrow points to the value of the attribute of the object. So basically, your starting of the arrow points to the object, and the end of the arrow points to the value of the attribute of an object, right? So in this case, it is okay. G23 is your object, and the value of the attribute of visiting teams is comes. So this is fine. If you see the second arrows about score, so in score also, if you see, score is the attribute and its value is 5 3, and the object is G23, right? So this is also fine because the object has to be on the left hand side of the arrow, and the value of the attribute should have been on the right hand side. But if you see the third one, just see the Dodgers one. Here, I think that this arrow is basically placed wrongly, right? Why? Because if you see, the object is basically on the right hand side of the arrow, basically on the end of the arrow. This is not correct. The object has to be on the starting of the arrow, and the arrow should point towards the value of the attribute of the object. So this is wrong actually. It should be, the arrow should be from G23 towards Dodgers. Okay, you can correct this. I'll correct this out in the slides, and then while uploading the slides on Google Classroom, I'll correct this. I'll correct this basically. Okay, is it okay now, Rishabh? I answered the question. Yeah, fine. Okay. Are you able to understand, students, how to convert a non-binary predicate into a semantic network? Getting or not? Okay, fine. Then other thing is, present a declarative sentence. Okay, so a simple declarative sentence you can represent using binary predicates only. But if you have a sentence like this, just see here, John gave the book to Mary. Okay, here you are saying John gave the book to Mary. So here John is the subject, Mary is the object, but what is this book? And the verb is giving, but what is this book? So can anybody tell me? Basically, it is having multiple classes, you can say, or multiple objects. John is also one class, Mary is also one class, and you have a book also, right? So again, it's a relationship between three objects, or you can say the relationship of giving is between three arguments, isn't it? It's again a similar scenario as a non-binary predicate. Why? Because you are having a action of giving, so your attribute can be giving, okay, but it is between three arguments: John, Mary, and book. Right? If you would say like this, John gave to Mary, then you would simply say that the verb is giving and the subject is John and the object is Mary. So in that case, you could represent. So in that case, you could represent it like a binary predicate, right? So if you have only John gave to Mary. So in that case, it would be simply represented as a binary predicate, right? But here you have John gave the book to Mary. So you have an additional object book. So basically, it's a non-binary predicate now, right? So if you take the attribute as relationships, uh, so relationships basically become your attributes, right? So relationship is basically your verb, basically. Okay. So relationship is basically a verb. So your verb becomes your predicate, right? So giving is your predicate, but it will have three arguments: John, book, and Mary. So that is an example of a non-binary predicate again. So then again you have to basically how you will represent it in a semantic network. Again you have to create a new object, okay? And that new object will be connected to all these three arguments: John, book, and Mary. Okay. So the same thing you have to do here also if you want to represent a declarative sentence which has got non-binary predicate representation. So that you can represent again using a semantic network in the same way. So you have to create a new object for giving. Okay, so giving is your basically the gist of this story is basically the scenario of giving, right? So what you do is you create a main object for giving. So EV7, I've just taken any name actually. EV7 is an instance of giving. Okay, why I have taken an instance of giving? Because it's a particular instance that John is giving to Mary a book. So a particular scenario I'm talking. It's not a general giving. It's a particular scenario. So I have to take an instance of giving. So give is basically my object, and I've created an instance of that object, and I'm calling it as EV7. Yeah, so basically, why haven't we considered give as an attribute, right? So if you see here in this scenario, what have we done? There was a game which was being played, so you have taken the game as an object, right? So the game was an object to which all the three arguments were connected. So if you take this, basically this game has to be taken as an object only. Otherwise, how you will formulate the relationship with the other objects? So whenever such a non-binary predicates occur, in that case, the main scenario or the main predicate becomes an object only. Okay. So in this case, your game was the object. You were playing a specific game. So game had become your object. In this scenario, giving is your main thing. This particular sentence is talking about giving. That is the main thing, right? Other things are basically coming out of it, that who gave it, and then to whom it was given, and what was given. So those are basically the branches, but the main thing is that it is the action of giving, right? So that give is basically becoming your object. If you don't take it as an object, if you don't take this giving as an object, you cannot have the three arguments related to this, because always the arguments become objects and they are related to this particular predicate through a relationship or an attribute. So attribute or relationship always occurs between two objects only, right? Between two nodes only. So that is why this giving also has to become one node only. Okay, if you take giving as an attribute, then you will not be able to take a relationship between all the three: John, Mary, and book. So you're taking this give as an object, then only you can relate it to all the three. Okay, so that's why you're taking this giving instance. Yeah, so that's why you are taking this giving and you're taking an instance of giving as EV7, just one instance you have created, and now easily you can basically connect it to all the three arguments. So it's a non-binary predicate. You have three arguments: John, Mary, and book. So you can easily connect this to all the three. So if you connect it to John, so John is the agent. So your attribute name would become agent. Then beneficiary is Mary because you are giving the book to Mary. So the attribute name for Mary, how it will be connected? So Mary is connected to giving through the attribute or through the relationship beneficiary. Okay, so that is the name of the attribute we have written for the connection between Mary and the giving action. Okay, and then your object is the book, right? And you are giving a specific book. In this case, you're talking that John gave the book to Mary. So that is a particular book which John gave. So again, you have to generate an instance of that book, BK23, let us say, or physics book or chemistry book, anything, basically any title. So that's has to be a specific book. So that is why I have created an instance of this book as BK23, and to that instance, I'm relating this instance giving, because it's a particular instance of giving and it's a particular book which John is giving. Okay, so that is why I have created the instance of book also, and now I have related it, and the relationship name or the attribute name is object, because giving an object to Mary. So agent is John, beneficiary is Mary, and the object which is being given is book. So like this you have given the attribute names. Now here also One more thing here, students, this is not a double arrow actually. It will be a single arrow, and that arrow will be from EV7 to the Mary, to Mary. Okay. So this is also, please, I'll correct this out. It's not a double arrow, it's a single arrow from EV7 to Mary because of the same reason. Because of the same reason that you have on the starting of the arrow, you have the object, and on the end of the arrow, you have the value of the attribute of an object. So that is why it has to be the arrow from EV7 to Mary. Okay. Uh, any confusion, students? How did we convert this into semantic network? Any confusion? Okay, one question. Any confusion, students? Please ask. Otherwise, I'll ask one question. Okay, if no confusion, then I will ask one question. Okay, so the question is, so if you see this example, this is also a non-binary predicate representation, right? And if you see this example, this is also a non-binary predicate representation. So then what was the difference that here you have taken G23 is a game. Okay. So here you have taken a class inclusion. G23 is a game. But here you have taken this EV7 as an instance of giving. So there is a difference between the two. This is a and this is instance relationship. Why this is so? Why this is so? Can anybody think and answer that there is a difference in this? The previous one we had taken the creation of that specific game, we had marked as class inclusion relationship. But here the instance of giving that we have marked as a class membership. Why? Any answers? Anybody can think of? See, there is a simple answer for this one, and it is basically a subjective answer also. It is not a very specific or a very crisp reason because it depends upon your understanding also of or it depends upon your domain knowledge also. But actually, you can understand it like this: that game is basically there can be many games actually, right? And you are talking about a particular G23 game. So game class can have many games. So G23 is one particular game, right? So out of the whole set of games, G23 is one game. So that is why it's a class inclusion. Because in the set of games, there can be many games, and G23 is one of those games, right? So G23, if it is there, it will be a game only, and there can be other games also. So it's a class inclusion relationship. But if you say the instance of giving, you are particularly talking about particular instance of giving. So it's basically an action. Giving is an action, right? You have the whole scenario basically. So you are basically giving is basically an action. It's not an object that have multiple values actually. If you say game, it can have multiple values. You can have a badminton game, chess game. Games can be anything. But if you're talking about a particular G23, it will be included in that set, right? But this is an instance of giving because it's a particular action of giving. So you have created an instance. It's just a member of giving class. It's a member of the giving class. It's not included in the giving class. It's a member of giving class. So it depends upon our understanding of how we are basically interpreting the objects. How we are interpreting the objects. It depends upon that understanding that how do we mark these attributes. So giving the attribute name as an instance or ISA or agent or beneficiary, it depends upon our understanding and interpretation. Okay. Are you able to get this, students, or confused? Anything? Getting? Are you able to understand what I just said? Students, please respond yes or no. Getting or not? Okay, fine. So if you are able to get this, fine, okay. So if you are able to get this, then we'll move on to the second declarative sentence representation. So basically, any sentence like this, if you give, then you can convert it into a semantic network representation, right? Now let us say I want to represent this sentence, one has height 5'7". Okay, this is another declarative sentence which I am giving to you. So this is a simple sentence. You have an attribute height and the value of the attribute is 5'7" and the object is John. So simple representation. This is a very simple example. You can write it like this. Just see on the right hand side, you have John is the object and attribute on the arrow is height and the right hand side node is 5'7", which is the value of the attribute. Right? So this is very simple conversion into semantic network. Then the other sentence is Bill has height 5'3". Okay, so this is also simple. The same way, Bill is the object, 5'3" is the value of the attribute, and our attribute is height. So you can create a semantic network for this one also very easily, right? Now, this is the declarative sentences given to you, and you have created the semantic networks for this one. But sometimes when you are given a declarative sentence, you don't need to create a new semantic network. Okay, sometimes it happens like this that you can just give some links and your sentence would be represented. It's not that every time you have to create a new semantic network. Okay, for example, if you see here, John is taller than Bill. This is a sentence which you want to represent. Okay, so first of all, you had represented these two sentences. John has got height 5'7", and the other sentence was Bill has got height 5'3". Okay, now you want to represent John is taller than Bill. So you already have two semantic networks with you, okay, and they are representing the individual heights of Johns and Bill, right? Now, if you just take another arrow and you put that attribute as greater than attribute between 5'7" and 5'3", so it's basically representing that John's height is greater than Bill's height. Okay, so basically, if you want to represent this declarative sentence, John is taller than Bill, and you already have two semantic networks, you can just link those semantic networks and you will be able to represent that sentence. So you have not created any new semantic network, just you have created one more arrow, and that arrow is basically linking the two heights, and that arrow attribute is greater than attribute. So you understand here from here that John's height is greater than, that means 5'7" is greater than 5'3". So basically that is John's height, Bill's height. So that is the greater than relationship you have established between 5'7" and 5'3". uh, Manual or decided by the system? What is your question, Nitin? What is manual?
Ma'am, I was saying when we
Yeah,
pass this sentence, John is taller than Bill, then it will be in
yeah,
binary predicate logic, taller, John, comma, Bill. But we have changed it into
yeah, yeah.
GT greater than 5'7", comma 5'3". Ma'am,
Okay,
we
yeah,
are changing it or the
yeah.
system itself is changing it?
For the system,
Ma'am, are we changing it or
what
the
did you say the
system
last
itself is
sentence?
changing it?
What change?
Ma'am, we will pass only the
No, no.
John is
See,
taller than Bill this sentence
yeah,
only.
yeah.
Yes.
Okay, okay, got it. So basically, it's not that any change is occurring. It's basically through inference that it is finding out that these are John's heights and Bill's heights. See, because you have in your semantic network, when you convert these three sentences into predicate logic, you will have a connection. You will have a connection between the John's height 5'7" and Bill's height 5'3", right? So you will have the predicate logic representations for these two sentences also. From that, it is obvious that 5'7" is the height of John and 5'3" is the height of Bill. So if you are having a relationship between 5'7" and 5'3", that 5'7" is greater than 5'3", then from that you will get 5'7" is greater than 5'3", and through inferencing you already have the predicate logic representation that it is the John's height 5'7", and 5'3" is the Bill's height. So then you can basically by inferencing you will come to know that John's height is greater than Bill. So it's not that system is doing anything. It's already fed into the system as a set of facts. So that fact is already existing that the height of John is 5'7", and other fact is also existing that Bill's height is 5'3". Now you have inserted another fact that 5'7" is greater than 5'3", so it will automatically link that 5'7" to John and 5'3" to Bill, and then it will infer that okay, John is greater than Bill. That means, so it will be inferenced. Okay. So it's not that anything is done by the system. Through the facts which are there in the system, we are doing some inferencing in order to decide that what you want to say, basically. Whatever you want to say, that is represented in the set of facts only. Through that only we are inferring. Okay. Fine. Okay. So this is basically, I just wanted to tell you this thing that whenever you have some sentences, it's not always required that you create a new semantic network. From the existing semantic networks also, you can basically create new relationships to tell you or to basically express the new sentences. So new sentences can be expressed just by creating relationships between two existing objects also. That's what was the concept for this slide. Okay. So this is basically how do we work with semantic networks, how do we convert the predicate logic representation into semantic network, and how do we work with non-binary predicates, right? So this was the basic concepts of semantic network, and then we have another concept, partitioned semantic networks. So basically, till now, whatever we have done is a predicate logic representation and converting it into semantic network. But the predicate logic representation that we have considered till now, we have not used any quantifiers, right? Till now, we have not considered any sentence which has got quantifiers in it. John gave the book to Mary. So we have not considered any quantified expression here, right? So it's a simple declarative sentence. But suppose you have quantifiers in your sentence. Then how do we represent it through a semantic network? So that is the next thing. And that we do through partitioned semantic networks. So it's a simple way of representing quantified expressions in semantic networks. So what we do is for representing quantified expressions, we have to partition our semantic network into a set of spaces. Okay, and whatever we partition the network into a set of spaces, and wherever we want to say that this particular variable is universally quantified or this particular variable is not quantified, so you have to create a different space for that. So the spaces which are there in one particular box, that will be corresponding to a set of quantified variables, and the spaces which are not there in that box, which are outside that box or maybe in some other space, that will belong to the non-quantified variables. Okay, so basically we basically partition our semantic network into a set of spaces, right? Some spaces are quantified, basically some the variables which belong to some spaces are quantified, and the variables which belong to the other spaces are not quantified variables. Okay, so that is why we say that it is a partitioned semantic network. So we'll take an example to tell you that how a partitioned semantic network actually works. For example, you want to represent this sentence, the dog bit the mail carrier. Okay, this is the dog bit the mail carrier. So mail carrier, he was carrying the mails and the dog has bitten him. Okay, so here there is no quantifier actually, right? Here there is no quantifier because a particular dog and he has bitten particular mail carrier, so it's there is no quantifier here. Okay, so this is a non-quantified expression. So without partitioning also we can represent it easily. How? So like this, see the A part of this figure. So just the A part of this figure, students, it's basically representing the sentence. The sentence was the dog bit the mail carrier. Okay. So here also you have basically you could represent it like action of link between dog and the mail carrier also. So basically, if you want to represent it as a binary predicate, that also could be done here, right? For example, you could say like this, that byte dog comma mail carrier. So it will, in the predicate logic format, it will become like this, byte bracket dog comma mail carrier, right? So in the semantic network format, it will be just two nodes, and the byte would be the attribute name on that arrow, and on the starting arrow it will be dog, and on the end of the arrow it will be mail carrier. So that will be a simple semantic network, right? So that is also possible here because it's a simple statement which has a subject and an object and a verb. So you can represent it in a form of a binary predicate also. But if you want to represent it in the form of a this statement, this kind of a semantic network, it's also that is also fine. That is also possible. So what we have done here, this is a slightly different version of a binary predicate. It's a binary predicate only, but a slightly different version. So what we have done here is we have actually considered writing also an object. Okay, so we have considered three objects: dog, byte, and mail carrier. So three classes, basically, three classes of object: dog, mail carrier, and byte also we have considered as an object only. Okay, that is why you got three boxes, three nodes. So D is a dog, B is a biting event, and M is a mail carrier. but it's not a natural representation actually, because natural representation is generally we take the verb as the attributes, okay, and subject as the first argument and object as a second argument means the right hand side. Instance is shouldn't it be instance, okay, okay, instead of all you are talking about instance of what, all three or which one? B. Okay. B is an instance of bite. Okay. B is an instance of biting. Okay. So, yeah. So, Nitin is saying basically that if you have this B, so you have created this. So, first of all, students, please understand this thing that it could be like this also. That first of all, I'll tell the thing which I was telling, then I'll go to your question, Nitin. Okay. So what I was telling was that basically if you consider it as a verb, biting is a verb basically. So in that case, it's a simple representation. You don't need to have three objects. But in this case, we have assumed that biting also is, we have assumed it as an object. That is why you got three nodes. Okay. So now you got D as a dog, M as a male carrier, and B is a biting event. Okay. Now you have related these three objects through the relationships. So B is related to D through the assailant relationship, and B is related to M through a victim, because male carrier was the victim, dog was the assailant. So dog was biting male carrier. So dog was the assailant, male carrier was the victim, right? So that is why the attribute names are assailant from B to D and victim from B to A. Okay. Now the question that that you are having within is basically that whether you can take B as an instance of biting, right? So biting is an event, and as we have taken here, just see this example with you in the previous slide. This okay, this one. So see here, students. So I have taken this one is a game, and there could be many games. So I have taken G23 is a game. Okay, because game is superclass of G23. Now, if you see here, this was an action giving. So I have taken an instance of EV7 as an instance of giving action, because I'm talking about a particular instance that John was giving the book to Mary. So it's a class membership relationship. So if you go by this logic, that your verb basically which is occurring, that is an instance of this give object. So if you go by this logic, then here also biting is a verb only, right? So it should be like, you can take it like B is an instance of biting. Okay, if you go by that logic, that verb is based, because we're talking about a specific instance only. The dog has bitten the male carrier. And this is very similar to that sentence. This sentence. So John gave the book to Mary. And this sentence is the dog bit the male carrier. So these are similar sentences. They're talking about a particular event which has occurred. So in this case also, you can basically use a instance relationship. So it can be like this. B is instance of biting. Okay, it can be like this. But actually, the logic, the concept which I want to explain in the partition semantic network is, I want to tell you that how do we represent the quantified expressions. So this is not important that what is the relationship name. You can put an instance relationship also here. It doesn't, in this case, that is not the focus of our example basically. So it can be an instance also. B is an instance of biting, D is a dog, and M is a male carrier. That is okay. D will be a dog only, because it's not an instance of a dog. It's a because the, or you can say it's this also, if you want, you can take an instance. So you can have instance attribute also in place of is attribute. That depends upon how you are interpreting it. Okay, so how you are interpreting it, you are interpreting it as a class membership or a class inclusion. So in that case, you can take an instance also. Fine, Nathan? Yeah. So the main logic that we want to basically that I want to explain here is how do you represent the quantifiers. Okay. So this first A part is a non-quantified expression, because it's a simple sentence, simple declarative sentence. It doesn't have any quantifier. Now, so it will be represented simply B, an arrow from B to D and an arrow from D to M. Right? This is the simple representation of sentence. The dog bit the male carrier. Now let us say you have a sentence, every dog has bitten a male carrier. Now here you are having every dog. So every dog means it's talking about all dogs. So there is a quantifier here, and that quantifier is a universal quantifier. So in this case, you will have to represent it through a partition network. So basically, how do we do that? Using a, first of all, you have to convert it into predicate logic format, and then you have to represent it in a partitioned network format. So you have to create two partitions. One partition would have non-quantified expressions, other partition would have quantified expressions. Okay. So if all the basically if all the variables are quantified, then you will put them in one box, and if some variable is non-quantified, you will put it outside the box. Okay. So we'll study how do we do that. Basically, how do we create the partitions of a network, and how do we represent the non-quantified and quantified variables separately in a partition network. So that we will study in the next class, which will be Monday. Right. So we'll continue it in the next class, students. All these three examples will continue in the next class. Divya, have you taken the attendance? Okay, Divya, please mail me today's attendance also and yesterday's also. Yeah, yesterday's attendance also have not received, Divya. And one more thing, I have not received the attendance of 11th February, Divya. Okay, please check. You might be having it saved somewhere. So please mail me the attendance of 11th February and yesterday and today. Three attendances. Yeah, please check out. You might be having it saved somewhere. That is not there with me. So that means you have not mailed it to me. Okay. Yeah, so students will meet on, and students, one more thing, you have a quiz tomorrow. I hope you remember. So you have a quiz tomorrow at 4 o'clock, right? You are aware, I hope all of you are aware. So tomorrow at 4 o'clock, right? Okay, fine. Yeah, yeah, I'll share the slides of predicate logic, and I'll also share the slides of that knowledge representation basics introduction which I had given. I'll share it. Okay, I'll do it today only. Fine. Okay, thank you all of you. Anything you want to ask? Okay, fine. So thank you all. Thank you.